Hi, this video is about some examples involving impulse and the change in momentum. So let's say you're trying to catch a water balloon. We have Isaac and James both trying to catch a water balloon thrown at them. Let's say the balloons are identical in size and they have the same speed and they both come to rest. But there's a difference in the two catchers here. For Isaac, he slows the water balloon down pretty quickly and it ends up busting in his hands. James gradually slows the water balloon down and safely contains it. So, I've got a question here, or three questions really. Which person's balloon experiences a greater momentum change, greater impulse, and greater amount of force? So let's start with momentum change. I've already written down the momentum of the balloon before and after to make it easier here. So the change in momentum going from 10 to 0 here is a change of minus 10, right? That's the change in momentum. For James, it's the same. It goes from 10 to 0. And so again, it's a minus 10 for the change in momentum. So we say delta P, change in momentum, is the same for both of them. So to answer that question over here, it's the same. Now, if you remember, impulse is equal to the change in momentum. There's an equation that we've written down before. I'll write it down again here. The impulse on an object, Ft, is equal to the change in that object's momentum. And so change in momentum and impulse are the same, so I could just replace this change in momentum with the product of force and time, and I would get the same thing. The impulse is also the same for these two balloons, because impulse and momentum change are equal. Now, the last question says, which one experiences a greater force? And while they have the same amount of impulse, F times T, the difference is for Isaac, he catches it very quickly, and so he uses a very small amount of time. I wrote the T really small to emphasize that the time is very small. In order to have the same impulse, though, it's going to have to be a very large amount of force. So we have big force times a little time. Over here, we have a longer time, so I'm going to write a bigger T for time, and as a result, a smaller force. So what ends up happening here is you multiply force times time and you get 10. Force times time, you get 10. So the product of force and time is the same, but the actual amount of force is not. And so which balloon experiences a greater force? That would be Isaac's balloon, because he takes a much shorter time to catch it, and so that requires a much greater force. So while the impulse, force times time, is equal, they're both negative 10 for the impulse, the amount of force can be different based on the amount of time that it takes to catch. All right, let's look at another example. Actually, let's look at a few examples of this. It's a very big idea in our modern technology, using this idea of impulse and momentum change. If you can extend the time of impact, then you can reduce the amount of force needed to change an object's momentum or to stop an object. So if you can find a way to extend the slowdown time, then it reduces the amount of force that's required to slow the object down. So a trapezist swinging above on a swing here, you'll find a net underneath them, because the net can slow them down more gradually than the ground. So if you took away the net and they just ran into the ground if they fell, then that ground is a very solid, it's a very quick end, and so it's a very high force. But a net can bend and slow you down gradually, and so it's a lot safer, less force required. Another example, and I tried to draw this, but it's not a great drawing. I don't know if you've noticed this before, if you've been like just watching in your car, but as you get near concrete barriers, you'll always find these metal collapsible barriers in front of them. And that's on purpose. These metal barriers that go often in front of these concrete barriers are there to slow down any cars before they hit the concrete. Concrete is very hard and it doesn't allow your car to slow down very gradually. It's pretty quick and sudden. So before you run into the concrete barrier, if you run into this collapsible metal barrier, your car can slow down gradually before it hits the concrete barrier. And hopefully it slows down so much before it even hits the concrete barrier that it stops and doesn't have to hit the concrete. So you'll see different variations of that. Cars themselves are very flexible and they bend a lot when they crash into other cars. And that's on purpose too, so that they have a greater amount of time to slow down, reducing the amount of force that it takes to slow them down. Sticking with cars, airbags are an example of slowing you down more gradually than, for example, hitting your head against the steering wheel or the windshield of the car. If you get into a crash, an airbag will slow you down more gradually because it's softer, and so it takes more time, which means less force acting on you. And by the same logic, basically any kind of cushioned object, like a goalpost that has a foam cushion around it, it slows you down more gradually, and so there's less force required. Doesn't hurt as bad to run into something that's cushioned. So anytime you can extend the time of impact, you can reduce the amount of force it takes to slow you down. So let's look at another example. This is a little bit different of an example because now we're dealing with two different objects, or people in this case, where they have different momenta going into the change. So we have two divers, Rachel and Gwen. Rachel dives from a taller height and Gwen dives from a shorter height. That means when they hit the water, they're going at different speeds. Rachel's going to be going faster and so has a greater momentum when hitting the water. Gwen has a lower momentum. Both of them come to rest in the same amount of time. So the questions here says, which diver experiences a greater change in momentum, a greater impulse, and a greater force? So for the change in momentum, we look at their initial momenta here, 30 and 10, and it says both of them come to rest. And so the change in momentum for Rachel is going to be 30 or negative 30, slowing down, coming to rest. And the change for Gwen is going to be negative 10. So Rachel has a greater change in momentum. And the change in momentum is equal to the impulse. And so Rachel also has a greater impulse experienced. And because she has a greater impulse, they have the same amount of time that they slow down in. That means that Rachel also experiences a greater force. All right, let's look at one last example. Here we have two bowling balls, 5 kilograms each, and they're dropped from the same height. Ball A hits the ground and bounces back up at 3 meters per second, while ball B remains stuck to the floor. It says here the collision time with the ground is the same for both balls. Which ball experiences a greater change in momentum, impulse, and force? So same question, different situation here. So at first glance, you might be misled here. Whenever an object bounces, it's actually experiencing a greater change. If you think about it like this, if you want to add some numbers here just to make it a little bit more clear, let's say that the momentum of this ball going down is 30 kilogram meters per second going down. So I'm going to say a negative because it's going down, downward direction. They both are negative 30 going down. But ball A bounces back up. This one, it says it bounces back up at 3 meters per second. So 3 times 5. That means it's going to have a positive 15 kilograms times meters per second going back up. Whereas this one has, this one has 0 momentum at the end. So which one has a greater change in momentum? Well, the change in momentum is the final momentum minus the initial momentum. So in this case, it's going to be the final momentum is 15 minus the initial momentum, which is negative 30. So we have a change of this negative, and negative becomes a positive, 15 plus 30. That's a change in momentum of plus 45 versus ball B, which is just 30 to 0. And so that's a plus 30. So ball A has a greater change in momentum because if you think about it logically here, the ball is not only stopped by the ground, but bounced back upwards. It takes more of an effort to not only stop the ball, but to bring it back up. There's more of a change there than just simply stopping. And so ball A has a greater change in momentum. And because of that, ball A also has a greater impulse exerted on it. 45 versus 30, so it's the same. And then the amount of force for ball A is also greater because it has the same amount of collision time with the ground. So that's all I've got for you in this video. Remember, a bad attitude is like a flat tire. You won't get anywhere until you change it.